So one of the interesting things that tie-ins with statistics and these things that we've been calculating is this idea of probability. Because statisticians rely on probability to make decisions when they look at the statistics and the things that they analyze. Now, this is not that unusual because each of us do the same thing when we make decisions in our own life. We kind of calculate the probability of this happening or the probability of that happening. And so probability is something that's kind of built into us, and we're used to making decisions based on probability, and we're even used to kind of calculating rough probability. So for instance, we might look at a situation and say, hey, that it's likely to happen that this thing will occur, or maybe there's no way that this certain outcome is going to happen based on just our gut feeling or what we know of the situation or things like that. So we're dealing with probability all the time. Now, we talk about, so in this chapter, this is chapter 13, we talk about chance, right? So chance is this percent of the time that something is going to happen, will likely happen if this thing occurs many times. So if you roll a regular six-sided die with the numbers 1 through 6 on it, the chance that you will roll a 3 is going to be 1/6. That's not to say, which is about 16.6 or 16.7% of the time. That means that you will, if you roll this dice many times, then about 16% of those times you're going to get a 3. It does not mean that on a given roll you could get anything on one given roll, but if you do it a number of times, it's going to happen about 16% of the time. And this is what probability is all about. It's understanding that if we do something many times, things will start to behave predictably. We know that chances are measured by percentages that are between 0 and 100%. So there would never be a chance or a probability of something occurring that is 150%. It just doesn't happen. Something that has a 100% chance is a certainty. It will happen. Something that has a 0% chance is an impossibility. It will not happen. And then you have everything in between to calculate. And so when we start talking about probability, we look at some real simple situations, right? So we look at things like flipping coins and drawing cards and rolling dice and things like that. So let's just look at a couple examples here and just to kind of get you the feel for these things. So for instance, if I've got a box, okay, so I can't see what's inside the box, but I know that the box contains it's got red marbles and blue marbles. Okay, so that's the thing. It's got red marbles and blue marbles in it, and we're going to draw one marble out of this box, and we're going to do it at random, which is to say we're just going to fill in there. We're not going to be able to look and see. And if it's red, then we win $1. Okay. If it's blue, then we win nothing. All right. So we have two boxes. All right. So we have box A that looks like this. It has 3 red marbles, and then it has 2 blue ones. Remember, we win $1 if it's red. We win nothing if it's blue. And then we have box B, which has 30 red marbles, and then it has 20 blue marbles. So we might want to ask ourselves, should we play this game by drawing from one box or the other? Okay, which box offers us the best chance of winning? Well, we can calculate our chance of winning, and you're probably pretty familiar with this. So you'd say, look, my chance of winning, I have 3 red out of 5. Right? 5 total. So 3 is the number of red, 5 is the total number. So that's my chance. If I convert that to a percent, of course, we could go through the whole process. It's 0.6. Do that on our calculator, right? 3 divided by 5, and then of course it's 60%. So the chance of winning from box A is 60%. Now does it change here? Well, to win, there are 30 ways to win, 30 red marbles out of 50. And of course you guys are already ahead of this, and you see that, hey, that's the same number. That's 0.6. That's 60%. So the chance that we win from either box is still 60%. So it doesn't matter that the numbers change. What matters is the ratio, right? The ratio is the same in both cases. It's 3 to 5. In the second case, it's 30 to 50, but if we reduce that, it just becomes 3 to 5, right? And so we do a lot of classic problems, again, just to get us thinking about probability. All right. So let's suppose we're going to draw 2 tickets from at random. All right. So let's look at another situation. So sometimes we understand probability, but sometimes it's easy to make ourselves a little confused with it. Okay. So let's look at this situation. Suppose we're going to, now you need to know what a standard deck of 52 cards looks like, right? So this is something you might want to look up if you're not familiar with, because we use a lot of examples involving standard decks of cards, right? So there are 4 suits: aces, hearts, clubs, and spades. They run from ace as a 1 up to 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen, right? So you know that how that works. So here's the situation. We've got a standard deck of cards, and we're going to draw from a shuffled deck 2 cards. Draw 2 cards. Okay. And basically, here's the game. If the second card you draw is the Queen of Hearts, let's write it in here, we win, I don't know, it doesn't matter how much, let's just say we win $100. If the second card is Queen of Hearts. Okay, so think about that for a second. I mean, if we were just drawing 1 card, and we won if it was a diamond, for instance, that'd be pretty simple. We'd just say, hey, look, diamonds win, so there are 13 diamonds out of 52 cards, so 13 over 52 is 1/4. The chance that I win is 1/4. But with this one, because the card is the second card, it seems kind of confusing, because think about all the things that can happen on the first card. You could have a 7 of clubs and then your Queen of Hearts in order to win, or you could have a 6 of diamonds and then a Queen of Hearts, and you would win again, right? There are lots of ways to win, because man, you can have lots of different things in that first card slot. And so this is an example of when we think about probability, it's pretty it's easy to confuse ourselves and make the problems difficult, right? And so if we start listing all the possibilities and thinking, okay, let's count how many times we win, we're going to get really confused. But in reality, we sometimes we can make it much simpler. And in this problem is kind of interesting because if we don't care what's in the first slot, right? We don't care what's in the first slot as long as it's not the Queen of Hearts. If the Queen of Hearts is in the first slot, then we lose, right? Because that means it can't be in the second slot. So all we need to know is, how many what is in that second card slot? Well, it could be anything, right? It could be any one of the cards. But we only win if that second card is the Queen of Hearts. So we say, look, there are 51 slots, right? In the second, if I take a standard deck of cards and shuffle it, there are 51 cards that can show up in that in that second slot. Now I say 51 because we're pretending that Queen of Hearts doesn't show up there, because if it's the first one we're done. There are 51 cards that show up in that second slot. Well, it could be the Ace of Diamonds, it could be the Three of Clubs. There are 51 ways that we can get a second card, in that slot. Well, how many of them are winners? One, right? Only the Queen of Hearts is a winner. So see, if I think about all the things that can happen in the first slot, I can make myself very, very confused and make the problem much more difficult. But in reality, I can make it simpler if I just look at it that way. I think that I actually need to come back here. This should be 1 out of 52, right? There are 52 cards that can go in that second slot, and the only way we win is if we get Queen of Hearts in that second slot, and so that's how we get 1 out of 52 is the chance of winning. But now here's an interesting follow-up. So let's change the question. What if the first card is an 8 of Diamonds? What are the chances of us winning? Well, so now this is where we come along and we say, look, first card is an 8 of Diamonds, so that's done. So we can almost pretend that, hey, we're dealing with a 51 card deck. The 8 of Diamonds is already out there, and the card on top, the next card that we draw, needs to be the Queen of Hearts. There are 51 of those cards left because the 8 of Diamonds is already done, and now there's only one way to win. That's if the Queen of Hearts shows up. Okay, so we see that the probability changes if something happens first, right? If we've already got the 8 of Diamonds, then we know the probability of winning is 1 over 51, which is better than the 1 over 52 we calculated originally when we didn't know what was happening in that first card slot. So this is an example of what we call conditional probability. We are calculating the probability of something occurring given that something else has already happened. Right? Now in this case, we see that the probability changed. It was originally 1 over 52, now it's 1 over 51. And so it changed because of the event. And what was the event? That we knew that the first card we drew was already an 8 of Diamonds. Okay, so another example maybe of conditional probability to think about is something like this. Let's just calculate here. We'll make it simple. The probability so let's talk about rolling a regular 6-sided dice. Rolling a 1 on a d6, so a 6-sided die. Well, all of you know that that's going to be 1 out of 6, right? But let me do a conditional probability first. In other words, let me say something has already happened. So here's what I'm going to tell you. So suppose I tell you, so maybe you roll this dice behind a screen. You don't see it. You know, only I see it. You're blocked out. So you roll the dice, you can't see the results, I can see them, and I look at it and I say, hey, look, I'm not going to tell you what it is, but I am going to tell you you've rolled an odd number. So this is like I'm telling you an event has happened. You've got an odd number that you've rolled. So the question then is, again, what's the probability of rolling a 1. We're still finding the probability of rolling a 1. But something has occurred. I tell you that you've already rolled an odd number. Well, so in your head you're saying, look, so if I rolled an odd number, so that means it could be a 1, 3, or 5. And so the probability of it being, so there's only 3 possibilities. So there's a 1 out of 3 chance of rolling a 1. So notice how the probability changed from a 1/6 to a 1/3 based on the fact that something had already happened. And I had to tell you what that was, what that condition was, but the probability changed as a result. Okay, let's look at another scenario. Suppose I have a box, and it's got a red marble in it, and it's got a white marble, and it's got a blue marble in it. Okay, we're gonna draw 2 of these marbles without replacement. So this is a term that you got to get used to. So if they say without replacement, that means you're going to draw a marble, look at it, put it in your pocket, right? And so the next time you draw, you're going to draw from only 2 possible choices. That's without replacement. If we draw with replacement, that of course means you draw a marble, look at it, put it back in, mix things up, and then draw again. Okay, so that's with replacement, without replacement. So the question is this: draw 2. Okay, so draw 2 of these marbles without replacement. Okay, without replacement. What is the chance of drawing the red marble, then the white? What is the chance? Red, then white. So in that order, right? And think about all the ways we can draw, right? You know, I could draw the blue one first, and then the white one, or the blue one and the red one, right? All the different combinations. But we want this one particular, red then white. Okay? So the way to think about it is this. First of all, we ask ourselves, hey, does it... So what we're going to do is we're going to first of all find the probability of drawing a red. Okay, well, that's pretty easy, right? I think we all can look at that and say, hey, look, there's a 1/3 chance that I'll draw a red. So a third of the time I'm going to draw a red ball first. Okay, well, now that red is gone, so now you're just left with whites and blacks, okay, or whites and blues. And so if I'm drawing again, now the probability of drawing a white is 1/2, right? So those are some probabilities that I can think about. So half the time I'm going to get the white one on that second draw. A third of the time I'm going to get the red one on the first draw. And so what we're going to use is a rule called the multiplication rule. And that just says simply, you can multiply these two individual probabilities together to find the probability of them both happening, like we said. So of course 1/3 times 1/2 is 1/6. That's the multiplication rule. Okay, and so again, this problem could be really complicated. I mean, when you think about all the different combinations, but if we just kind of think our way through it, we're able to maybe kind of simplify it, and that's going to be a really important skill that you develop as you work through these homework problems. So the last idea you're going to encounter in this chapter has to do with an idea of independence. Okay, now independence is this idea where we think about 2 things happening in kind of succession. Event A happens, and then event B happens, and basically those 2 events are either independent or dependent. They're independent if if what happens with event A doesn't affect what happens with event B. Okay, so let me give you a simple example here. So suppose we're going to toss two coins, right? So the first thing I'm going to do is flip a coin. So we can either flip two coins or flip one coin twice. But I want you to just think about that for a second. Does what happened, so if on flip one affect what happens on flip two? I think you would pretty easily see that, hey, they don't affect each other, right? What happens on the first flip really doesn't change the probabilities on the second flip. Each time I flip the coin, the probability of getting, say, a heads is 1/2. So it doesn't matter if I got heads on the first one or heads on the or tails on the first one. The two flips are independent. Okay. So the probabilities don't change. Okay. So that was a fairly simple example. Let's try another situation. Suppose I have these four numbers or these five numbers in a box. So 1, 1, 1, 2, 2, and 3. So I have those numbers in a box. All right. And we're going to make two draws. We're going to draw from this box at random. And we're going to do it with replacement. All right. So first we'll draw twice with. So the question is this: suppose the first draw is a 1, or sorry, is a. Suppose the first draw is a 1. Put a little circle around it. The question is, what's the chance of getting a 2 on the second draw? Okay, remember this is with replacement. Draw 2. Okay, so we draw the first time. It's a 1. Great. We look at that, we put it back in, and then we draw again. Well, what's the probability of getting a 2 on this second draw? Well, because you replaced the one you originally drew, there are 2 2s out of the 6, so it's a 1/3. Okay, so notice the probability of getting a 2 is still 1/3. Didn't matter if I drew a 1 to begin with. Let's try again. So now, because remember what we're trying to study is we're trying to understand if what happens on the second draw is affected by what happens on the first draw. So let's try another first draw. Suppose our first draw is a 2, and again with replacement. What's the chance of getting on our second draw a 2? Okay, so we draw a 2 on our first draw, we look at it, we put it back in, we mix things up, we draw again. The probability is still 2 out of 6 equals 1/3. So see, look, it didn't matter what happened on the first draw, the probability on the second draw stayed the same. Okay. It was still 1/3, so those events were independent. The first draw and the second draw are independent. Now, what if I change it? Change one little thing. And the thing I'm going to change is, let's draw 2 without replacement. So what do we get on the first one? What do we get on the second one? So let's look at the same scenarios. Scenario 1 is the same. First draw is still a 1. What is the chance of getting a 2? Well, remember, this is without replacement. So draw first one, grab it, look at it, put it in my pocket. Now what's the probability of getting a 2 on our second draw? Well, there's still two 2s in there, but now there are 2 out of 5. Okay, so that's the probability now. But now let's look at the second one. You have to look at another possibility, and that is, suppose our first one is a 2, and what's the chance of getting a 2 on the second draw without replacement? So we grab a 2, take it out, put it in our pocket. Now, what's the probability to get a 2? Well, there's only one 2 still in there out of the 5. So look, the probability changed from 2/5 to 1/5. So in this situation where we were doing it without replacement, these two events, the first draw and the second draw, are dependent, right? What happens on the first draw affects what happens on the second draw. Okay, so we do this all the time. When we look at a couple of events that happen at the same time, we say, does the one event happening change the probability of the other happening? If they don't affect one another, then they're independent. If they do, then they're dependent.